Good morning, afternoon, or evening. My name's John, and I'm going to address this comment that was posted on a video that I did a few weeks ago during the Advent of Code peer review video, where I made a claim that the assembly code generated by a method that uses nested for loops versus one that uses an iterator system is going to produce the same assembly code. And so this person says, "Hey, I have a hard time understanding how the assembly could possibly be the same." And so I want to sort of address this, and I'm going to back out of my claim a little bit because I have not been able to produce code that does have identical assembly, but we're going to look at that and show like how one would do that, and really what the differences in is between our hand coded for loops and using an iterator system. So let's get going. So I'm going to use benchmarking and disassembly to be able to illustrate what's going on here. So the function that I'm doing here is I have a two-dimensional grid. I've defined a grid here as a vec of x, where every character is a period. And I'm setting the very, very, very last element to be this at sign. This is a typical sort of advent of code problem where you have a map, a grid, something that you need to find an element in there. So I'm making this two-dimensional grid, and then I have a bunch of different implementations of this that is going to find the location of this at sign inside of this two-dimensional grid. Now, these are vecs of x, meaning that each row is going to be allocated individually. This is not an actual contiguous two-dimensional array of data. We could certainly do that, but in this case, it's a vec of x. And actually, I might talk about what it looks like when we do have an array. But my implementations ended up building a data structure that looked more like this. So let's look at our first for loop version of this function. So I often am calling this an old school way of doing an iteration through a container. This is how we're taught in really CS 101, at least when I did it. I'm not going to go back into how long ago that was, but I'll just say it was the first year that our school, Purdue University, was teaching C++. Prior to that, our freshman computer science was learning Pascal. So anyway, that dates me a bit. So in this case, we have our outer loop that's going through all of the rows, the inner loop that's going through all the columns. We have an X and a Y index, and we index into this grid and check to see if the grid that we're looking at matches the value that we are looking for. And if it is, we return that X by location. Otherwise, we return none. This is very clean. This is what we sort of expect to see. This is how most of the world is going to write a find routine to look for an element inside of a for loop. I'm going to see if I can reorient my screen so we can see both the, well, actually, let's just scroll down and look at the iterator version of this. So my iterator version looks like this. I am taking in a grid, and I'm using some generics here, but they're sort of functionally similar to to what it was before. And I'm actually going to have sort of another video that's talking about the evolution of going from a more statically typed function to one that's using generics. And I'm using this as an example, so I'm already starting to go into the ASREF. So our function or our operations look like this. We get the iterator from the grid slice, and we enumerate on that. That's just going to that's going to give us a positional element for every row in that. So what is now returned is a tuple where the first one or the zeroth element is a a U size of the row that we're on, as well as the row data itself. Row, we get the ref because this is an simple as ref of an array of chars. We get the ref version of that. We get the iterator of that. We enumerate again. That's going to give us the X value, as well as the cell value for each one in there. And we check and we filter on that to see to get only the values that match this predicate, where the predicate is, does the cell equal what we're looking for? If it is, then we're going to return the XY location and we get the next. This arguably is very, this is not intuitive to read. That does not mean that this is not easy to maintain. But this is what I'm going to call our first iteration of an iteration of how we are going to walk through the grid in iterators. And if we look at the types that are here, iter is going to return this. We don't really care what that is. In the flat map here, we have y, that's a U size, and each row is going to be a reference to something that can give us a reference to a character slice. We are taking that apart and we get finally a X value that's the U size, a cell that's a reference to the value that's in there, and we do the check. Like even just saying that makes it sound very challenging to understand. But let's first look at the benchmarks. So here is what the benchmarks look like for all of the different functions that I have. So our for loop is the first for loop that we looked at. This is using for y and the range of the rows, for x and the range of the columns, and we get the cell and we return it. And that took 34 milliseconds to go through a 1000 by 1000 grid and find the very last element. Our iterator version of this took 23 milliseconds, faster than the for loop, which really seems surprising, considering the level of sort of abstractness that is being done. I really thought that I could hand code something using indices and be faster than an iterator version of that. And it's not. It just isn't. And so let's look at the assembly code. Well, actually, the assembly code is different. Let me bring up the assembly code to show you what I did. Here we go. I'm using the compiler explorer. This is godbolt.org. And I pasted in the code that I have here. The versions of the files that uses for loops. For loop grid is trying to, for loops row is trying to use some unsafe versions of it to see if I can eke out some more speed. The answer is I can't. The benchmarks show that they're pretty much identical. I believe the assembly code is identical. And here's my iterators version and some alternate versions of my iterators that I'm also benchmarking. Over here, I am generating assembly code for the ARM64 processor. And I'm using the ARM64 processor just because it's a little bit easier instruction set to look at to try to see what's going on. And so the way that we're going to see here is we're going to see, especially because I have the inline never. Inline never is just saying we are not going to generate, we're not going to be able to pull this function in line with my test code here that is it's calling everything. It will inline what's inside of here, but not the function itself. So in the assembly code, we can find, if I find it here, There is a lot of code here that is for doing panicking and debug stuff, but here is the assembly code for the for loops. And in this interface, you can like find the assembly code that represents these different instructions when you want to decode that. I might go through something that is going to give us a like a breakdown of how the assembly code is written. But the for loop assembly code looks like this. Goes all the way down to here. The for loop row, I believe it is the identical assembly code. And here's my iterator version, which, if we look at this side by side, looks like this. So for loops is on the left. I've copied and pasted this into VS Code to be able to see this sort of side by side. In most of this, there's going to be a little bit of a preamble where they're where it's moving things around to get the registers set up before it's going to start looping through through the answer. It is hard to find commonality between these two. At some point, there's usually a compare and a branch down to the end to return. These are so vastly different. The code for the for loops is very, very different than the code with the iterator. So my claim that I made in the YouTube video that they're the same is a complete falsehood, except the fact that they produce identical results in actually more assembly code. So, I mean, you can't just count assembly codes because you have to look at where the tight loop is and how many instructions are actually being executed. But the iterator version is 41 lines of assembly code. The for loop is 31 lines of assembly code. I would venture to guess that the for loop is very much in line with a direct translation from indices into adding and subtracting and doing it manually, where the iterator version is not. It'd be really interesting to break this down, to watch the machine execute this and see where the real differences are. So I want to wrap this video up because it's actually gone a little bit longer than I wanted it to go. But this whole file here, we have several versions of this, and they all do the same thing. This for loop version, a for loop that is trying to cheat the compiler to do unsafe versions of accessing the rows. This is my first iterator version, which is attempting to have the same sort of signature as the for loop, except being fully iterator based using this method where we're doing a flat map and we're getting next. This is another version of it. I'm using find. So I do find map and enumerate through the rows, and I do a find map on the row, and I get that. The inner like predicates are the same. We're just using find map instead of filter map and flat map instead of find map. It's different, and it actually runs slower. Why? Again, you'd have to disassemble the assembly code and take a look at that. Here's another one that uses positions. So instead of having an inner one that does enumerate and find a map, we use position to find the position of that and get the XY. This actually just takes out the enumerate on the inside and converts that into position. This does produce the identical assembly code from the from I forget which one it was. Anyway, and then let's see, we have the very last one here, which is a fully generic version of this. And this is more in a tutorial going into decomposing this into something that is doing generics where it can find anything in a two-dimensional grid of iterable things. In this one, I am using the position version of it. I believe the inner code is almost the same here, but we're just getting the iterator of the outer version, and we're finding the position of the internal version of the iterator. Fully generic will work for anything that has iterable, a nested iterable system with the inner type, the fully inner type that will do a partial EQ on it. So look for that video as we kind of take this and turn this into this fully generic one. I think that will be a really good one to look at if you're interested in learning generics a little bit more, especially generics for something that can do any sort of find in any sort of container that has this two-dimensional iterable sort of thing. And this version is actually one of the fastest ones that runs in our whole system. So even though it's fully generic, this runs faster than our hand-coded nested for loop. Really interesting. Cool. So yeah, ran a little bit longer than I thought, but I think there's some good information here, at least to go down some other rabbit holes to see what else you can find. Have a great day.